And let's get right into question 1. So a liquid-liquid separation is a method used in organic synthetic chemistry to help purify a solid or liquid compound. So there's 2 different types of techniques you can use, either washing or extraction. The main difference in between the two is what layer you keep and what layer you discard. The main thing to note about this is that the solvents used in washing or extraction must have limited solubility in each other so they appear clearly separated so you can separate the compounds from each other. So let's talk about extractions. So an extraction is used to separate an organic acid or base from an organic neutral compound. You will either remove or keep a component using a solvent. Each compound in a solution will prefer residing in one of 2 immiscible phases. The aqueous solution, which will either contain your organic acid or base, and the organic liquid, which will contain organic neutral compound. You can determine the identity of the liquids from looking at their densities. The denser of the liquid will be at the bottom of the separation flask. You can temporarily increase an organic compound's polarity by making it ionic, which will make it prefer the aqueous phase more from the organic phase. So this figure from page 63 of the lab manual shows an already polar carboxylic acid. It is reacted with the base to produce an even more polar conjugate base. This more polar conjugate base will prefer the polar solvent more, which causes it to separate from the mixture into the aqueous layer. Now your desired organic acid is separated from the solution mixture. So here is a model I've created to explain this extraction. So a polar solvent is added to the organic liquid. This organic liquid, in this case, contains an organic neutral and an organic acid. They are mixed in the separation flask. After mixing, the organic acid is separated into the polar solvent, and the organic neutral remains in the organic liquid. Since this is an extraction, you want to keep the isolated acid and discard the organic neutral in the organic liquid, unless Dr. Luong says otherwise. Sometimes you want to keep the organic liquid. Always read your instruction manuals. Alright, let's get to washing. So washing is the removal of contaminants from the layer of interest. In this case, would be the organic liquid. You want to remove the immiscible solvent from the solution to remove impurities such as wood chips or other contaminants you would find in the solution. Much like in the extraction, in the washing, you still want the solvent and the mixture to be immiscible because you want to separate the 2 different liquids. Taking a look at the model that I've created, there's an organic liquid that contains an organic compound and impurities. A solvent is then added, and the impurities must be soluble in the solvent for the washing process to be effected. The solution is then mixed in a separation flask, and the impurities are separated from the organic liquid into the solvent it is soluble in. You want to then discard the solvent since it contains the impurities and keep the organic liquid since it has been washed of these said impurities.
Hi, my name is Rexy, and I'm wondering how to separate a homogeneous mixture.
Thanks for asking that, Mr. Poodles Doodles. That leads me right into question 2, how to separate a homogeneous mixture. I was given the second homogeneous mixture, which contains anthracene, piperidine, and oxalic acid. So first, you want to dissolve the homogeneous mixture in benzene as the solvent. I did some research and I figured out anthracene and piperidine are soluble in benzene, and so they will dissolve in that mixture. Oxalic acid, however, is insoluble in benzene. So you want to pour the solution into the gravity filtration, like right here in the model, to separate the oxalic acid from the mixture. After running that through the gravity filtration, you'll have your isolated product, oxalic acid, separated from the rest of the mixture. Man, I wish the rest of the steps were this easy. 1 out of 3 done. Now we have a solution containing anthracene, benzene, and piperidine. What you want to know is that benzene solubility in water is low, 1 milligram per milliliter. It can be considered negligible, so we can say that benzene is water insoluble. Next, you want to add a strong base, such as like sodium hydroxide, to the solution, which will cause the piperidine to ionize, becoming more polar. Next, you want to add this solution as well as water to a separation flask. Mix 5 to 6 times, open the cap, and let the mixture separate. This is where the extraction occurs. as I have detailed in my model. So the ionized water-soluble piperidine will be pulled into the water, which is then creating the aqueous layer. The water-insoluble benzene and anthracene will remain in the organic neutral layer because they are water-insoluble. Now there may be a question, which layer is which? Well, the answer is density. A denser liquid will be at the bottom of the container. Since water is more dense than benzene, you will find your aqueous layer at the bottom of the separation flask and your organic layer at the top. Next, what you want to do is separate the two liquids into two different beakers. So the organic layer may contain trace amounts of residual water from the separation flask. So you want to add a drying agent such as brine to the solution to remove residual water. To get rid of the drying agent, you decant the solution to separate it from the brine. Next, you want to go to the rotovap. Since the boiling point of benzene is 80 degrees Celsius, we'll be able to remove it via the rotovap. Beware, you'll have difficulties removing solvents that have a boiling point above 100 degrees Celsius. So, you want to put the solution in the rotovap, and in about 5 to 10 minutes, let's say, the benzene will evaporate out of the product, leaving your isolated anthracene. 2 out of 3 done. Let's go. Alright, now let's isolate the piperidine from the aqueous layer. You want to do this step as quick as possible to prevent side reactions from occurring. So you want to cool the aqueous layer in an ice bath and put a stir bead in the beaker and wait until the product precipitates. Give it some time and precipitation will occur due to the product being in the ice bath. To collect your final precipitate, you want to use suction filtration by using a Buchner funnel, which will remove the water and the base and will isolate your final product, piperidine, as shown here in the model. All the impurities that you do not want get sucked into the chamber right here, and now you're left with your final product, piperidine. We have an isolated piperidine, anthracene, and oxalic acid from a homogeneous mixture. Alright, now we've made it to question 3, talking about the organic synthesis experiment. And before we can begin to talk about the procedure, we should at least talk about the objective, which is to synthesize 2-butoxynaphthalene and determine the product purity. 2-butoxynaphthalene is used as a strawberry and raspberry flavoring agent. And my puppy Rex, you love strawberries, huh? Well, he's gonna go find some strawberries, look for the flavoring agent. There you go. Alright, time to talk about the procedure. So, add 3 pellets of sodium hydroxide, half a gram of 2-naphthol, a stir bead, and 5 milliliters of 95% ethanol to a distillation flask. Make sure the distillation flask is clamped, or else you have a safety hazard on your hands. Put the condenser on the flask and boil until all the solids have dissolved. It takes you about 15 minutes or so. Then remove the condenser, add half a milliliter of 1-iodobutane. Add this 1-iodobutane using a digital pipette. After this, put the condenser back on and let the liquid boil for about an hour, hour and a half. Near the end of the reaction, you want to take a sample of the reaction mixture and perform a TLC experiment using the eluent ethyl acetate to hexanes 3:1. Use 2-naphthol as the S spot on the TLC plate to compare the product to ensure the reaction has occurred properly. After the reaction is done, you want to do the workup phase, which is the isolation and purification of your final product. So you want to pour the flask contents over 10 grams of ice in the beaker. Make sure to keep the flask contents cold, or else the product will melt and you will lose your product. And that is bad news. Since the product precipitates, you want to isolate the pure product via vacuum filtration. Weigh the amount and determine how much product you've made, record an IR spectrum, and finally store in a labeled sample vial. And there you have it, that's the procedure. Alright, time for an analysis of our product 2-butoxynaphthalene. So let's compare its experimental IR to its literature IR spectrum to ensure that the identity of the product is indeed 2-butoxynaphthalene. So this is the literature IR spectrum for 2-butoxynaphthalene, and this is the experimental. So by comparing the two spectrums, both signals have a band peak at 3050, which is characteristic of sp2 carbons bonded to a hydrogen, which would be those hydrogens in those 2 aryl rings. They also have signals at 1630, which is a characteristic of a sp2 carbon-carbon double bond, which would be those carbons in those aryl rings. And just by comparing the two spectrums, you can see that they have signal peaks around the same wave number. For examples, they have same signals at wave numbers 2950, 2930, 2870, and 1510. But those are just few out of the examples. If you compare both spectrums, they have band peaks at pretty much the same wave numbers. This analysis tells us that the product indeed is 2-butoxynaphthalene because the IR spectrums of the experimental and the literature are the same. By using 2-naphthol as the S spot, the bottom new spots all have the same RF value, indicating the product still contains components of the starting material, meaning it did not evaporate out, indicating the desired reaction occurred and the desired product we have. The higher new spots in the R and CO spot indicate impurities in the product, such as the leaving group iodine or other impurity components. Alright, let's get right into part C. So the organic synthesis of 2-butoxynaphthalene is determined to be a SN2 mechanism. This was determined by looking at the hour reflux time when the 1-iodobutane was added. So the reason for the long reflux time, which was about an hour or so, was because the solvent that was used was ethanol, which is a polar protic solvent because it has a hydrogen bonded to the electronegative oxygen, making it polar protic. However, SN2 mechanisms do not like that. They prefer polar aprotic solvents because it maintains the high nucleophilicity of the nucleophile. Since the solvent is polar protic, the nucleophile does not maintain its high nucleophilicity, which is why the reflux time of the reaction is as long as it is, because the partial positive of the ethanol reacts with the nucleophile instead of the substrate, which reduces the rate of the reaction. Now, if we use the polar aprotic solvent instead of ethanol, I'm sure that the reaction time would be faster than it is.
But Carter, what is the nucleophile in the reaction?
Oh, I thought you'd never ask, Rex. This is why I created a model. So here in step 1, the OH- ion from the sodium hydroxide deprotonates the oxygen from the 2-naphthol, turning the 2-naphthol into a good nucleophile. This is shown in step 1 here in my model. Now in step 2, the nucleophile 2-naphthol attacks the substrate, 1-iodobutane. Since this is a SN2 mechanism, the leaving group iodine leaves at the same time that the nucleophile attacks the substrate, which in turn then produces the product 2-butoxynaphthalene and the leaving group iodine. Here's the transition state for the mechanism, which will illustrate the characteristicness of the SN2 mechanism, where the loss of the leaving group occurs at the same time as the nucleophilic attack, which is what the SN2 mechanism is, showing in this transition state. The 1-iodobutane is a good substrate because it is not sterically bulky, so the carbon center is easily accessible to the nucleophile so that the substitution reaction can occur more easily. The iodine is a good leaving group because it is electronegative, so it can stabilize the extra negative charge. The 2-naphthol is a good nucleophile because of that charged oxygen, which can easily attack the substrate's carbon. Alright, question 4, let's go. First, let's talk about a common way to purify solids. We can do this through recrystallization, which is a solid is dissolved in a solvent and then it's precipitated out. So the first step is solvent selection. You want to choose a solvent that won't dissolve the solid at room temperature, but it will dissolve the solid when heated. Once you've found the correct solvent, you want to add the solvent and the solid to an Erlenmeyer flask, heat to the solvent's boiling point. Do not add too much solvent. Next, you want to perform a gravity filtration to remove substance impurities. You want to perform this process as quick as possible to prevent premature crystallization. The recrystallization solution is then poured onto the filter paper in small amounts, bit by bit. The solution will then go into the Erlenmeyer flask and on the hot plate, leaving behind impurities. Time for crystallization. So first you want to cool the solution to room temperature. Once it reaches room temperature, then put it in an ice bath. Crystals will then form. The best quality crystals are formed without disturbance and when you allow it to cool gradually. This will produce the largest crystals. That's what you want. Now finally, to isolate the crystals. Isolate the crystals via vacuum filtration, which will separate the desired solid from the unwanted liquid. You want to wet filter paper with solvent and put it in the Buchner funnel. Next, put it on the suction flask and make sure it's clamped. No safety hazards here. Add the solution to be filtered out in small portions, so then the liquid will get sucked into the isolation flask. And your isolated solid will now be in the Buchner funnel with no liquid. Let it stay in the vacuum filtration for 5 or 10 minutes so it comes out nice and dry. Let's talk about the melting point determination technique. So the experimental melting point is a great determination of a substance purity and its identity. You want to compare the experimental melting point to a literature value so you can figure out its identity if it's impure or not impure. So you want to determine the melting point range, which is when the substance begins to melt, which is called the onset point, to when it is fully melted, called the clear point. A pure substance will have a sharp melting point range of 1 to 2 degrees Celsius. The substance will be impure if the melting point is lower and broader compared to the literature value. So to do a melting point determination, you want to put your sample in a watch glass and then poke the melting point capillaries into the sample. You then want to put the capillary in the heating apparatus and record the ranges. Simple distillation! Why? This is why. Number 1, it quickly removes the solvent left behind or concentrates a solution. 2, purifies a volatile liquid because components are separated according to their boiling point. Make sure to use substances that have low boiling points because let me tell you, it's going to be tough to heat up a substance that has a boiling point of like 300 degrees. Just so you know, weak intermolecular forces give rise to gases. Strong intermolecular forces give rise to liquids or solids. Well, what is used to overcome these forces? One word: heat. Most common during the lab, you either want to separate a liquid from a dissolved solid or separate two liquids that their boiling points differ by more than 100 degrees Celsius. Let's talk steps. 1. Heat is supplied to boil the solution in the distillation flask. 2. At the boiling point, the vapors rise up to the thermometer and go into the condenser, which cools the vapors and gives us a nice liquid. 3. Finally, the liquid runs down the condenser and the liquid drips into the collection vessel. Your boiling point range is then recorded. Compare these experimental values to literature values to determine the purity and identity. Remember, the narrower the boiling point range, the purer the compound. Pure substances have sharp boiling point ranges from 1 to 2 degrees Celsius. Let's talk Rotovap. It's like simple distillation, but cooler and newer. It also removes solvents from samples that have boiling points under 100 degrees Celsius. It consists of a cooling source, a vacuum source, and a rotary apparatus connected to a reaction mix vessel. The rotary apparatus rotates the reaction vessel. The hot bath heats up your solution, and your solution is connected to a vacuum and condenser. The vacuum reduces the vapor pressure of the system, so your mixture boils at a lower temperature. Wow, that's pretty cool. When the solvent leaves the reaction vessel, it immediately hits a condenser, which condenses the solvent for waste disposal. Now you have your pure product in the reaction vessel. Thin layer chromatography, let's go. So the stationary phase, silica gel is used in the lab, is spread over an aluminum backing. Then small spots of solution is placed near the bottom of the plate with a capillary pipette. This is known as spotting. The plate is then developed by putting it in a jar with a small amount of eluent. The eluent most commonly used in these labs is ethyl acetate to hexanes, 3:1. The eluent will creep up the plate via capillary reaction, which will also bring the solution spot up the plate as well. We can get 3 pieces of info from TLC. First, the purity. A compound will have a specific RF value. This RF value is calculated from the distance from the origin to the new spot divided by the distance from the origin to the solvent front, which is about a centimeter away from the top of the plate. This is a ratio to how far the compound has traveled relative to the eluent used. A compound is impure if it has numerous spots. These numerous spots indicate impurities. The second piece of info allows you to ID the component. Spots with the same RF value may hint that they're the same compound. A third piece of info, it allows you to monitor the reaction progress. You can compare an unknown to a suspect. In the co-spot, if the spots are the same, then they're most likely the same compound. because they have the same RF values. If the spots differ, then they're most likely not the same compound, and you gotta try again with the new suspect. You can visualize the new spots on the TLC plate by putting it under UV light. As you can see, all three spots are at the same spot, so they'll have the same RF value, meaning that they're most likely the same compound. IR spectrum time! IR spectrum allows you to identify what the compound is and determine its relative purity by comparing it to a literature IR spectrum. So you compare these two spectrums and you can see which signals are the same and which signals are different. So is the product that you've created the same as the literature, or it could be the same, but there's some varying signals due to the impurities in the compound that you have produced. So the IR measures the amount of light transmitted through a sample. So you put it on a spectrometer and it gives you a spectrum. On the y-axis is the transmission percentage, and on the x-axis is your wave number. On the spectrum, there are numerous bands. You want to know how to read these bands because it can tell you valuable information about the compound structure. So first you want to look at the intensity of the signal. If there's more of the same functional group, then it's going to have a more intense signal. Let's say there's a compound with 3 CH2 groups and a compound with 1 CH2 group. The compound with 3 CH2 groups will produce a more intense signal than the compound with 1 CH2 group. Next, you also want to look at the x-axis, which is the wave number, which tells you the identity of the functional groups present in your compound. So for example, if you get a wave number band reading around 1640 to 1820 wave number, that's a signature of the carbonyl group, and it has a quite strong peak. Now, if there's a signal between 2400 and 3400, then you're looking at a carboxylic acid, because it's a wide signal. Gas chromatography time! So the gas chromatographer has a column coated with a stationary phase, and then a sample of one or more compounds is injected into the column, and then it is pushed through by the mobile phase, which is the air. The compound can either stick to the stationary phase or be pushed through by the mobile phase and be in the mobile phase, depending on the strength of their intermolecular forces. Volatile compounds will spend little time in the stationary phase and most of the time in the mobile phase due to their low boiling points, which provides a low retention time. A retention time is how long it takes for the compound to exit the column, and this is how the identity of the compound can be determined. The peak height and area indicates how much of the sample has been injected into the gas chromatographer. Remember, gas chromatography is only useful for liquids. You can determine the identity and concentration of an unknown compound by comparing it to various standard solutions. And then by looking at these various standard solutions, you can see which retention times match up to the standard and the unknown. You can then plug these values into a standard curve and then calculate the molarity of the unknown. Now it's time to talk about liquid-liquid separation. So this can either be done by extraction or by washing. So for extraction, it's where two immiscible phases are in a separation flask, an organic layer and an aqueous layer. The denser of the two layers will be at the bottom. You want to add a strong acid or base to the solution so that it'll ionize the acid or base and make it more polar, so it will be pulled into the aqueous layer. Washing separates the impurities from the solution, but you want to make sure that the two liquids are still immiscible. Or how are you going to separate the liquids? So for liquid-liquid separation, you want to pour the two immiscible liquids into a separation flask. You want to put the stopper in, shake 5 to 6 times, unplug the stopper, and let the liquid separate. If you want the best results, we all want the best results, it's better to do multiple smaller liquid-liquid extractions than one large one. Once the liquids have separated, pour them into separate flasks, and boom, your liquids are now separated. Time to talk about drying agents. So after a liquid-liquid separation, in the organic layer, there might be some pesky residual water left over. This is evident if the mixture is still cloudy or if there's a layer forming over or under the solution. You may be wondering, oh, how do I get rid of this pesky water? The answer? Drying agents. Little did you know drying agents can come in many forms. Do you want 2 examples? Well, you're getting them. First off, we got potassium hydroxide. Potassium hydroxide is a good drying agent, but you can only use it when the organic is a base, an amine. On the other hand, there's magnesium sulfate, which is fast and useful and can be used for anything really. However, it is best filtered out of the substance because of its fine particles. You may be wondering, well, how much drying agent do I add? Well, the thing is, you add the drying agent until it stops clumping in the solution, until it's able to move freely. And then finally, to get rid of this drying agent, you can either filter the drying agent out or decant the solution, and boom, no more water. It is all gone.